Hello everyone, I am Mr. Philip J. Zhao, a second-year college student under the program of Bachelor of Secondary Education, major in Science. In this video, we are going to discuss about the series circuits, equivalent resistance on series. A series circuit contains one path for electricity to travel through. If a series circuit breaks in any place, the entire circuit stops working. In this bottom picture, the middle bulb is broken and that creates a small gap in the circuit. Now electricity cannot get from one side of the battery and through the entire circuit and back to the other side. So all of the light bulbs have stopped working. This is a series circuit, and you can see on the left here that electricity is able to travel through the entire circuits and all of the light bulbs are glowing. But when I open the switch, I create a gap in the middle of the circuit. Opening the switch in the middle of the circuit turned off all the bulbs. In a series circuit, it does not matter where the gap happens. If you get a gap anywhere in a series circuit, the entire circuit stops working. Now let's talk about the equivalent resistance on series. We describe the term resistance and explain the basic design of a resistor. Basically, a resistor limits the flow of charge in a circuit and is an ohmic device, where V is equal to IR. Most circuits have more than one resistor. If several resistors are connected together and connected to a battery, the current supplied by the battery depends on the equivalent resistance of the circuit. The simplest combinations of a resistors are series and parallel. Resistor in series. Resistors are said to be in series whenever the current flows through the resistors sequentially. Consider this illustration, which shows three resistors in series with an applied voltage V sub AB. Since there is only one path for the charges to flow through, the current is the same through each resistor, and the equivalent resistance of a set of resistors in a series connection is equal to the algebraic sum of the individual resistances. Take a look at this figure. The current coming from the voltage source flows through each resistor, so the current through each resistor is the same. The current through the circuit depends on the voltage supplied by the voltage source and the resistance of the resistors. For each resistor, the current through the circuit depends on the voltage supplied by the voltage source and the resistance of the resistors. Drop occurs that is equal to the loss of electric potential energy as the current travels through each resistor. According to Ohm's law, the potential drop V across a resistor when the current flows through it is calculated using the equation V is equal to IR, where I is the current in ohms and R is the resistance in ohms. So since energy is conserved and the voltage is equal to the potential energy per charge, the sum of the voltage applied to the circuit by the source and the potential drops across the individual resistors around a loop should be equal to 0. On the other hand, the sum of the potential drop of each resistor and the voltage supplied by the voltage source should equal 0. Now solving for I. Since the current through each component is the same, the equality can be simplified to an equivalent resistance or R sub S, which is just the sum of the resistances of the individual resistors. Equivalent resistance in series circuits. Any number of resistors can be connected in series, so if n resistors are connected in series, the equivalent resistance is. One result of components connected in a series circuit is that if something happens to one component, it affects all the other components. For example, if several lamps are connected in series and one bulb burns out, all the other lamps go dark. So let us practice this problem.
Okay, so let's try to solve this simple problem for resistors in series. So according to this example, so let's compute first for the equivalent resistance, then the current in the circuit, then the potential drop across each resistor. So we have here a voltage source given the value of 18 volts. Then we have three resistors. So this is R1, this is R2, then this is R3. So here R1, has a value of 12 ohms, your R2 has a value of 5 ohms, your R3 is just 1 ohm. Given this circuit diagram, we can say that the three resistors are connected to a series circuit. And this is because if we have a current, let's say current I, so this current I is the same for all my resistors. So therefore, in order to get the equivalent resistance for the resistors or a set of resistors connected in series, we just need to add all of their values. So R2 plus R3. So we know the value of R1, so that's just 12 ohms. Then your R2, which is a value of 5 ohms. Your R3, which is 1 ohm. So therefore, my equivalent resistance is equal to 18 ohms. So it's very simple. And it means that we can rewrite or re-express this circuit diagram as this. So we have still your 18 volts of voltage source. Then we have this single resistor, which is your equivalent resistance value, which is equal to 18 ohms. So both of this circuit diagram, so they are the same. They're equivalent to each other. The next thing that we want to calculate is the value of the current that will pass through your circuit. So for this case, given that this is a series connection of three resistances with a certain voltage source, so what we can do is we use your V is equal to IR formula, and we know that your I is equal to V over a certain R, wherein R the value of R here is your R equivalent or your equivalent resistance. So the value of your voltage source is 18 volts. So we have 18 volts here over the value of the equivalent resistance for this circuit diagram. Then we have 18 ohms. So the value of I for this circuit is equal to 1 ampere. So it's simple as well. So the last thing that we want to identify for this example is the value of the potential drop across each resistors. So in order to get that, we know the value of the current that will pass through this series circuit, which is just 1 ampere. We can use this value to calculate the voltage or the potential drop across each resistors. So let's say for the first resistor R1, the value of my potential drop of V1 is equal to I times R1. So I know the value of I, which is just 1 ampere. So R1 is given, which is 12 ohms. So therefore, my V1 or the potential drop across R1 is equal to 12 volts. So same goes with your R2. So I times R2. So this is just equal to 5 volts. Then for my third resistor, I have I, R2, R3. So this is equal to 1 volt.